In this presentation, we will present our work on low voltage energy efficient neural inference on embedded devices by leveraging fault detection techniques. There's lots of talks in recent days on convolutional neural networks and their application in different areas, in particular in IoT framework. But the question is that how these neural networks can be implemented in a manner that the energy consumption of them are manageable, so that we can supply the devices with a limited energy sources. The need for energy efficiency is endless, and our desire to increase the energy efficiency by a factor of 1,000, so we make independent energy supply independent neural inference possible. Historically speaking, Moore's law, which means shrinking the transistor size year by year, helps us to increase the energy efficiency and cost of manufacturing of the digital processors. But the problem with Moore's law is that it's reaching its end. At recent years, we are closing to 2-3 nanometer transistors, and the cost of manufacturing for this transistor is extremely high, and it's unknown that if we ever are able to go beyond the technologies, the process technologies that are demonstrated already. So the gain from the Moore's law is diminishing. On the other hand, the other approach is leveraging Amdahl's law, meaning that we leverage parallelism and other algorithmic improvements like pruning the neural network or quantizing the weights and operations. But the programmers have done almost whatever they could, and we consumed almost any method and any possibility that was possible, that was feasible to reduce the energy. Now, in this presentation, we are looking for an unorthodox way to reduce the energy consumption. So what is our approach? To give a background, I would like to mention the power consumption in digital circuits. The power consumption of digital circuits is made of two major components: dynamic power and static power. Dynamic power has quadratic relation to the supply voltage, and static power has linear relation. So, and a strong dependence on the voltage is observed here. On the other hand, it is shown that if we reduce the supply voltage of CMOS transistors to the near threshold, near threshold and sub-threshold regions of operation, meaning the supply voltage would be around 0.4, 0.3. Of course, these numbers are examples. They depend on the process. The energy efficiency gains are substantial, 10 to 20 times increased in energy efficiency. But the problem is that it's very, very difficult to model the behavior of the circuit at those reduced voltages. So the optimum frequency and voltage points are unknown. This is because we have a phenomenon. A phenomenon that is called process variations. When we are manufacturing the transistors on the chip, not all transistors are manufactured in the same with a similar characteristics. Some transistors happen to be a bit faster, and some happen to be a bit slower than others. This makes timing analysis of the circuit very difficult. So we are not able to determine the exact operating frequency for each chip unless we go through extensive testing, which is expensive. Now, on the other hand, many devices that are produced by manufacturers usually have some voltage margin on top of the best case operating voltage. Manufacturers are not able to test truly all the manufactured chips, so they add some voltage margin on top of the best operating voltage, let's say 10% to 20% of margin, to increase their yield. So all the produced chips will guaranteed to operate in the worst case condition. But the thing is, we are not operating in the worst case condition all the time, and 99, maybe 99% of the produced chips do not require to be operated with full scale voltage, and they can actually operate correctly with reduced voltages. But how much is this voltage margin? We don't know. Current chip design methodologies are too conservative. They want exact results, and for that reason, they put lots of margins, as I mentioned in previous slides, in different design stages. If somehow we can get rid of those margins, substantial power and power reduction will occur. Now the question is that, should we make the design approach more liberal? Should we design a digital circuit that doesn't auto-put correctly all the time? I don't think programmers will be happy with such a design. They want their code to be executed exactly as they programmed. But maybe we can relax some design constraint, conservative design constraint, if we have some form of regulator that guarantees the exact operation, or at least guarantees exact operation to a large extent. The conventional approach for this is to equip circuits with something that is called timing error detection systems, which simply is sampling output of combinational logic passes twice, and in the second time with a delayed register, and comparing the outputs. And if the outputs are not the same, then we deduce that there is a timing error. This is one of the methods. Of course, there are multiple methods from this family, but most of them are around this concept. Now, such a hardware techniques require a huge overhead in design time, and if not designed properly, huge overhead in the die area, and they eat away some of the power savings that will be achieved by reducing the voltage. If we want to avoid difficulty of making hardware-based error detection, we can use software-based approaches. Maybe we can detect errors in software and algorithm level. For a neural network, maybe we can have redundancy to the neural network, and then using this redundancy, we can detect if the neural network is operating correctly or not. And based on our detection, we adjust the voltage of the device that is performing neural inference. Our test setup in this work was an FPGA and a Zyng SoC that has a microprocessor and an FPGA, and we adjusted the supply voltage of the FPGA by sending PM bus commands to the DC to DC converters on the board. Of course, the methods presented in this presentation are applicable to any other processing devices that allow voltage scaling. Now, we utilized two approaches. In our first approach, we used some technique called self-supervised learning. We borrow this technique from machine learning community. What they do by supervised learning, they add a trivial secondary task, which they call pretext task. And they ask the neural network to do the pretext task next to the main task. And in this manner, they increase learning capability of the neural network. And in a manner, they force the network to pick more features from the training data set. Usually, these techniques have very, very low overhead, and we expect the prediction rate for the pretext task to be in correlation with the main task. So what we did, we trained a neural network to detect the numbers, predict the numbers, and at the same time predicts the rotation of the images. So that based on that rotation, which will be applied in the runtime during the inference time, we can estimate the accuracy of the pretext task when the voltage is scaled. So we scale the supply voltage of the neural network, and we tested for different small data sets for each voltage point. As you can see, the accuracy of the pretext task is in very good correlation with the accuracy of the main task. Notice that accuracy of the main task is not known in actual implementation, and we only have accuracy of the pretext task. So you see that this red plot here, when the voltage is around 0.78, the accuracy of the accuracy of the pretext task drops significantly. And from there, we can detect that the network suffers from computational errors, and we can stop reducing the voltage. And in this manner, we can release 20% of the voltage margin. Our second approach that shown to be very, very accurate and sensitive to errors is using algorithm-based fault detection. So algorithm-based fault detection is a family of methods that by augmenting the data, they can detect computational errors in the output. So for a matrix multiplication, the ABFT goes like this. If we have a matrix A and matrix B, and assume these blue elements are the part of the matrix A and B, and if we augment matrix A with an extra row that corresponds to summation of the all elements in their corresponding columns, and in the same manner we augment matrix B with extra column, that each element in the extra column corresponds to summation of the all elements in the corresponding rows, then it is shown that if we multiply such a matrices, the resultant matrix will contain the actual multiplication of A and B, and it will have it will have an extra row and an extra column that has exact same feature as A and B, in a manner that the summation of the all rows are equal to the elements of the last column, and summation of all columns is equal to the the elements to the in the last row. So we modified the convolution block of neural network to contain such a ABFT technique, and and we changed the hardware in a manner that when the input come, automatically the summations of the input are calculated and added to the input matrix, and after multiplication, the summations are checked to see if any error has happened. Using this approach, similar to the previous approach, we reduced the voltage by around 20%, and we detected even one single error. I mean, even if the accuracy of the network wasn't dropped, we were able to detect errors that were hidden, and they didn't show themselves show their impact in the accuracy. We reduced the voltage by around 20% again, and we could explore different voltage and frequency points based on the detections. So this amount of voltage scaling corresponded to almost half of the energy consumption on our FPGA. Of course, the leakage of the FPGA is relatively high because of extra logic and routing devices. So the scaling wasn't quite quadratic. However, this still showed a huge improvement. The same results are expected in GPU, CPU, and other computational devices. Now, our proposal was to operate the computing device in low voltage and utilize some fault tolerance techniques to enable safe voltage scaling. And in using this method, we shown that we can remove the voltage margins. Maybe in near future, we can explore aggressive voltage scaling to even near threshold and sub-threshold voltage domains, as ABFT approach and self-supervised learning approach were shown to have very good error detection capabilities. So the research question for future is that, are there any other software or algorithmic approaches in neural networks that makes us able to reveal errors in the computations and to leverage them to reduce the overall power consumption? Thank you very much for your attention.